Hello, I'm Yerim Shin, master student in VML, and then today I'm gonna review preprint named Synthesizing Physical Characters in Interactions, written by Hassan, Guo, Wang, Black, and Pang. I took video sources from supplementary videos that they provided a lot, so for more detailed result videos, please refer to that video. This preprint was just submitted last week on February 2nd, and I chose this paper to present because, as far as I know, there are few research about solving physical interaction problem through DeepRL, so I was quite curious about it. The contents are as follow. Virtual character to interact with different objectives and their surroundings is considered important fact to make character animation realistic. Despite this importance, most of recent research has explored it to a limited extent, allowing character to move around in relatively simple environments. Specifically for data-driven kinematic models, they are able to produce high-quality motion for synthesizing character-scene interactions. Yet, when applied to unseen environment, they often struggle to generate realistic behaviors that respect scene constraints. Physical-based models using reinforcement learning are better to synthesize plausible motion adaptive to new scenarios. However, it is well known that designing RL objectives is difficult, and also it is hard to apply to complex scene interaction tasks. Recently, adversarial motion priors (AMP) has been proposed for imitating variety of motions from large unstructured motion dataset. And this AMP utilizes adversarial discriminator to differentiate motion generated by policy and motion in the reference. And this property helps policy-generated behaviors to deviate as needed to adapt to new scenarios. In this research, they utilize AMP and extend it to character scene interactions. They propose framework for physically simulated characters to learn scene interaction behaviors from large uninstructed motion datasets without manual labeling. And from now on, I'll introduce the method. The framework consists of two main parts, policy and motion discriminator. The first component, discriminator, has a role of distinguishing policy-generated behaviors and motion dataset behaviors. And the second component, policy, takes a role of determining how the character moves in order to maximize reward RT. And wait. The objective of the first component motion discriminator is to find the parameters that minimize the following equation. This term was proposed by Pang in the paper AMP. And to be specific, the first term encourages discriminator to predict a score of 1 for a sample from the reference. And the second term encourages discriminator to predict a score of 0 for sampled recorded from the policy. And the last term is the gradient penalty introduced in AMP. This model penalizes non-zero gradients on samples from the real dataset to make training more stable. And by minimizing these three terms, discriminator is trained to differentiate between policy-generated behaviors from reference data. And the second component, policy, serves as generator in GAN, and the objective of it is to maximize the discount reward shown in the slide. By maximizing the equation, policy tries to produce motion that resemble behaviors depicted in the reference, while also completing the given tasks. And I'll introduce the reward function used in these equations. The reward function RT, 왜 이러지? At each time step is specified according to this term. What? I don't know why this image is here, but sorry. The total reward is divided into two parts, task reward and style reward. And the first term, task reward, encourages the character to satisfy high-level objectives such as sitting on the chair or lying on the sofa or moving an objective to the desired position. The second term, style reward, encourages the character to imitate behaviors from a motion dataset as it performs the desired tasks. And as mentioned above, the policy is trained to maximize the expected discount return JPI. And from now on, I'll introduce about state and action used in this framework. The state that are input of the policy and discriminators consist of character configuration and objectives in the scene relative to the character. The key difference from the prior work AMP is that the state includes object features, and this allows the discriminator to evaluate motion's realism with respect to the object. And the action, which is the output of the policy, is specified as joint target rotations for PD controllers. And for the motion dataset, they used SAMP dataset and their own mocap carrying a single box. SAMP dataset provides example of human scene interactions with only 7 objects, and carrying mocap consists of a single box. Nonetheless, their deep RL framework can naturally interact with far wider variety of objects.
Why did they use the motion of carrying single box when their purpose is to synthesize like a sitting on a chair and lying down on the bed? Why did they use the motion of single box carrying?
The tasks are consist of 3 tasks: sitting, lying, and carrying. So that's why they use the carrying a single box mocap dataset.
Okay, so I guess then their purpose is to prove that even if they use the only data set that reflects the one of the tasks, they can still do other tasks also.
Oh no, they trained policy for each task. So the one that they wanted to prove was that this data set only consists of objects of limited types of objects, like
Which is carrying a single box, right?
Carrying a single box, or SAMP dataset consists of 2 datasets, sitting and lying. And I think SAMP dataset doesn't have the dataset of carrying the box, so they mocap the yeah.
Okay.
I think that's why they use that mocap data. Okay. Is there any question?
Yes, I have one more question.
For
the reward, for the task specific reward, you explained that they specify like a sitting on a chair and they're lying on a sofa and so on. Then how do they actually specify the motion of sitting on a chair or lying on a sofa?
They actually give the reward term as follows, like this. Is it?
Okay, yes.
Yeah, they give the reward like this.
Okay.
Yeah, but I thought it was too much specific, so yeah. Okay. And if there's any other question, I'll continue. So, yep. Even though they use the limited data set of the objects, they contend that their DRL framework can naturally interact with a variety of objects. And I'll introduce about the result of this research. For the result, they shows 3 examples of scene and character interaction: sit, lie down, and carrying tasks. And as you can see in the video, character can smoothly switch motion from ideal to walking, and from walking to various task-specific behaviors. And with training of various objects, results shows that the policy-driven animation successfully adapt to various range of styles of objects. And also the character is able to behave in different styles while sitting and lying, such as jumping to sit on a high chair and leaning back on a chair or sofa. Now on, I'll introduce about those evaluation metrics they provided. To evaluate their method, they conducted 2 large different evaluations by measuring quantitative metrics for each task and by studying robustness of their policy to external perturbations. For quantitative metrics, they evaluated first the success rate, which records how many times character successfully completes the task objectives. And second, actuation time, which measures how much time it took to complete the task. And lastly, precision, which measures how far the character ended reaching from target location of sit, lie, and carry. And they insist that despite the diversity of test objects, their policies succeed in all tasks up to 90% of success rate. And they also measured robustness to the external perturbations, such as box projectiles and sudden changes to the environment. Despite upon confronting external perturbation, the simulated character showed that it has ability to recover and resume the task. And finally, they compared method for sitting tasks with 3 different models, 2 from kinematic and 1 from physics-based model. 2 kinematic models tend to produce non-physical behaviors such as foot skating and object penetration. Furthermore, since human demonstrations are learned without interaction with the environment, these models can struggle to generalize to new scenarios. Work of Chow is based on physics simulation. However, as you can see in the video, it frequently fails to sit on the target object. Finally, they also provided quantitative comparison to those, and as shown in the table, their method showed highest success rate among these methods. Lastly, I'll introduce about the discussions. There are some limitations, and at first, they use separate policy for each task, so multitask RL remains future work. And second, in some cases, character fails on completing the task within the duration of an episode. And lastly, the environment focuses on one object at one time. Nevertheless, they insist that there presents a method that can realistically synthesize interactions between character and scene in a physics-based way. Also, they employs discriminator while taking account of objects in the scene. And finally, actually I didn't mention in the slide, but they introduced randomization approach for physical properties of objects in the scene. And this is for my presentation. If you have any question, please tell me. Yes.
For training discriminator,
Mm-hmm.
they sample the state transition, but how can they sample with a fixed state as time step t+1?
I think I didn't get the question. Can you please say
In
it
the
again?
discriminator loss term, they sample from the data set as transition information, and their notation use the time step t+1. How they sample S and ST+1? They are random.
You mean how you make the sample from? You mean
S
how do
and
they?
ST+1, yes.
As I studied AMP, I think I don't know how this method sampled from it, but in the AMP that I saw in the GitHub, they actually do store this S and ST+1 in the buffer, and they sample from that. Can this be the answer for your question?
Yes, thank you.
Hi, I had two questions, and for the motion discriminator, does the input only the sole motion data? I wonder if it gets additional information about the size of the chair or other information about the environment, or just gets only the motion data.
Data, the one that
because my question is that I'm kind of curious that if this model can generate the motion that like if let's say if it wants to generate a motion about sitting on the chair, then if the sofa is kind of long, can it able to generate the motion that sits on the side of the chair, not in the center of the chair?
I think I got the point, and they get the input of the objects position and the object orientation. For only the discriminator gets the object position and the orientation, and the bounding box is like they are giving the input as a goal to the policy. So the one that you are curious about is going into the policy, I think. So the policy is generating the, so motion discriminator is to make the, make the data distribution similar to the reference data. And the policy is taking the role of seeing the scene and generate like the policy is
Yeah, I kind of get the role of each component. So for the policy, I think it's making the decision to train the reinforcement model to kind of make the whole proper motion. And I think the motion discriminator has a role of making that motion to be kind of plausible, similar to the data set. And I think the bounding box is kind of a additional information about the environment that where motion should be limited to. And I wonder if it can generate some kind of variations to the motion. Like when I look into the previous slides, there seem to have emotions like lying down on sofa, sitting on the chair. They seem to have located themselves in the middle of the chair, like
yes.
center. So I was wondering that if this model could like make the animation about sitting on the like edge of the chair or lying somewhere else. I think those kind of variation. If is it possible to make expect this model to have those kinds of variation?
Yeah, the task reward, I think the target position is given by the task reward, and the position is, I didn't read the exact reward function, but I think they gave them as a target position for the middle of the sofa or chair. So if you change that target position to the point, like side of the sofa.
Yeah, I think that
You
depends
can,
on the
yeah,
specific function that you
yeah,
showed. Yeah, so in the appendix, I think there was a,
yeah,
the function. So depending on how you write it, the specific function, the
right,
vector will behave accordingly.
Then it kind of depends on the reward function, right?
right,
If you define it as like much more various range to the target, then it would be possible to generate those kind of variation. Is it right? Okay, okay. And since the second question is that since I'm kind of new to this motion field, so I wonder if you could elaborate some distinctive feature compared to the previous study. So what is the big change in this work?
So they utilizes this motion discriminator, which was presented in the paper AMP. And the difference is that there, the previous paper AMP didn't look at the human scene interactions, didn't deal with the task of human scene interaction, such as like carrying boxes or sitting on a sofa. So they just only dealt with the problem of reaching to the target position or backflip or walking or running like that. I think that's the contribution of this paper, different from the AMP. And that was, I think, I think it, as I mentioned in previously, they included the object with respect to the character to the state. So they were able to also look at the scene information to interact with them. Is it?
Yeah,
Yeah.
I think I got the point. Thank you.
Oh, Ed.
Thank you for the presentation, and I have few questions. The first one is about the evaluation, where they measure the success rate and the error. So I'm also not familiar with this field, so could you maybe elaborate how to measure the success rate and the precision?
So for me, it was also the first concept that I saw for this metric. And in the paper, they said that a success rate is measured for the sitting task. They consider sitting to be successful if the character's hip is within 20 centimeter from the target location. Like, so I think they measured it from whether their hip or like a specific joint to be within the target position, like that. I think they kind of created this metric themselves reasonably. Can this be the answer?
That makes sense. So it's kind of like you get a target position that you want to sit on, and you're measuring the distance between the hip joint and the target position, right?
Yeah,
Okay.
and I think they made the threshold of that.
Yep. Okay. So my second question is actually maybe an extension from this. So they compare with Cow et al.'s method, right? But it seems like they're doing the same task, but why do they fail so miserably?
What can you say that again?
So they compare with previous methods, right? And one of the methods was from Cow and their colleagues.
This
Yeah,
one?
right. And you showed the table and their success rate, I believe it was like 20%, right? Or maybe not. Oh, 17%. So why is it so low, even though they're maybe doing the same task?
As I wait, I did not. Which one?
I'm guessing that probably the purpose of their paper is not something similar to
Yeah,
the paper you're trying to do, but then the reviewer asked them to do the comparison.
Maybe,
that's the
probably.
reason. Yeah, I think that's the reason. I thought that it's not fair, actually.
Oh, okay. So what does the Cow and their Cow's method do? Is it something different from this task?
I didn't really search about it, so after the seminar, I'll look at it. Yeah.
It's okay. And last question is regarding the reward. And I'm also not quite familiar with reinforcement learning. And it seems like in the method they're adding two rewards. And one was like style and one was task. And I'm not sure like how we're getting those rewards from. So it seems like the RS is definitely coming from the motion discriminator. So the discriminator is actually make like outputting some numbers to be calculated. But for the task reward, is it like computed using the environment and like some specific, what is it, things that you have shown in the appendix?
Yeah, they use it from it is
okay. Yeah,
they
okay, that
give
makes
the
sense then.
reward, yeah, right.
Okay, thank
Equation.
you. That was all. Thank you.
I have a question too. In the limitation slide, I didn't quite understand the second point.
So for reinforcement learning, there is an episode that the time step to, and I think they measure the time, a specific time. So 뭐라고 해야 되지? In the reinforcement learning, there is an episode that the agent do the action, and the episode is divided into time steps. So so the
I thought they showed all the successful result, but then somehow in the limitation they say they failed on completing the test. I thought they showed all this like successfully completing the test in the result section.
I think they wanted the character to reach to the target and like approach to the target and complete the task in the limited time duration. But sometimes they kind of tries to reach the target, but furthermore they couldn't complete the task, such as like, so they're far from the target, so they're approaching to the task, and I think they wanted the character to complete the whole process of approaching to the target, and then such as and then sitting on the target, that process in the limited time. But sometimes it had the failure on completing the task, such as like sitting, like finishing sitting on the chair. 뭐라 설명해야 돼?
I thought that one episode means from the start of the simulation until the completion of the task. There was the one episode. So the character did it successfully. So I'm a bit confused. They couldn't do it, within the duration of one episode.
As far as I know, the episode doesn't mean the start of the task and the end of the task. Episode is they give it as a fixed time step for the episode, and then if the character completes the task within the, so for example, if the episode is kind of user defined it as 10 seconds, and if the character finishes the task within 10 seconds, such as like 5 seconds, then the episode ends. So, but if the
So what you're saying is episode means user-defined fixed time?
Yeah,
okay, so my understanding of episode is a bit different. So I don't know. Okay. I thought the episode means the entire simulation time. Yeah, from the start of the simulation to until the end of the test. But then if it's not the case,
if the character,
why would it be important? Let's say user give the 5 seconds and then make the character to finish the task in 5 seconds. Why would it be important to do it?
maybe because the character maybe
is it because of the reward that you give, because you have this discount factor as the time progresses? So I mean, like, you can finish in the task within an hour, but if you finish it after an hour, it isn't really that meaningful. You have to do it as fast as possible. I think that's what the reward is designed like that. So I think that's why people usually define this episode to be like in a really short time, such that the agent can do the task as soon as possible, if I understand correctly.
So then if the model can make the motion sit on the chair, but if it's wander around about like 30 minutes and then go sit down, it's not what we desire, right? So we want the model to directly go to the chair and then sit down, and that's what we only need. And if the model generates unnecessary motion, we want to discourage that. So I think it's kind of,
if the character wander around, that means the reward will become smaller and smaller. So by design, you will try to find the optimal way to complete the task. So unless you don't have a data in the data set to satisfy the condition, you will not wander around unnecessarily, because that will violate the reward maximization.
So then for that purpose, the episode is like frame limit, right? Is it
it's time frame limit? It's frame limit.
I think like the episode definition of episode is kind of not well defined, as your IS professor is confused, I think. Yeah.
After I'll search for that and then tell. Yeah.
Okay, and then I have
later.
Another quick question. So it's a physical character interaction method. So where is the physics being considered in the construction of the method? So they are trying to compare the result of the method with the reference to make the style correct, and then try to enforce the given equation. So I'm wondering where the physics part come into play in this method.
The policy gives the action, and
Yes.
this action is defined as the joint target rotations for PD controllers. And this
Okay,
PD
here, here they use
controllers,
PD controller. Okay,
yeah,
okay.
yeah.
I missed this PD controller part here. Okay.
I have a generic quick question. So it seems like they're saying the method works well in very different scenarios. So I was wondering whether this kind of reinforcement learning can actually be extrapolated outside of the training data distribution. Because like if that's possible, I think it's a really good point. I mean, like throwing boxes to the character, I think that's kind of like extrapolating, but I'm wondering whether this kind of method can extrapolate within different interaction with the object. So let's suppose you have the training chair size, the chair height to be, let's say, 10 centimeters to 100. And my natural question is whether it can extrapolate to 150 centimeter chairs.
Oh, can you tell me the last question again?
Oh,
I think I
oh,
missed.
so my simple question is that
Uh-huh.
if the agent has learned to sit on a chair within, like, let's say 50 centimeters to 1 meters, right? Could it actually learn how to sit without retraining to a 1.5 meter chair? So can it extrapolate outside the data training data distribution?
As far as I remember, they say that they can extrapolate the to the different data distribution, but if the data is too different, they can't like deal with that a lot. Think in a limited range of data, they might be able to handle, but not much, not very different.
As a good another example, if you think about Kyungmin's paper, basically it's trained with the reinforcement learning. Then in this, one of the scene was like a dynamically changing environment. So it's a object obstacle avoidance test. The object is like a dynamically changing, and then you don't know where it's actually changing. So you cannot train with a fixed scenario, but still it can avoid the obstacle successfully, whatever obstacle configuration is. So that means it can extrapolate to unseen scenarios.
I think that's really the biggest benefit of reinforcement learning from deep learning model. Is there any question? If now, I'll end my presentation. Thank you.